Hello, my name is Yang Li. I'm the AP teacher here, and today we're going to continue our video lessons here. Okay, today we'll talk about the topics about the velocities and the rates of change. All right. So for this part is this. Actually, velocity is a concept of physics, and I got my bachelor and a master of physics, so I feel especially interested with this part. The velocity and the rate of change, they are like, connected to each other, okay? And remember before we learned about remember we learned about this one here? Oh, we just use the graph here, it's easier. So you see here, there is a graph here, this one here. Before we said any function, this is fx, right? And then we can get what? We can get slope of the secant line. So this is secant, right? See that? This is secant, right? And then we move this one from here to here, we can get tangent line slope, right? That's the time we think this is fx. But right now, if we are talking about something with what? Linear motion, okay? Like this question here, they told you that. They said we have ST. ST means the displacement, the position of the particles or moving objects at t time, okay? So average rate, that's just like a slope of secant line, ST, y2 minus y1, huh? Just like here, you can have this one here, just ST minus SA, y2 minus y1 over t minus a. So that's why they got this one, just like before we did about the slope of a secant line. And then for the instantaneous rate of change, that will be the velocity. That's we write it as the derivative of the function s at t equals a. That's a time what's the velocity will be. That's called the instantaneous velocity at the a. Okay, so that's this one. This one just like before we learned about slope of a tangent line. All right. So this is the one here. This is the basic concept though here. This is the basic concept. Now we're going to apply this one and use the explained about like 3.7. Okay, when you have 3.7 here, they told you that this is called the harmonic motion, the spring up and down, right? Harmonic motion, because this is the this is the ceiling, and then you have an object put here. This is the balance part. And then when this one, the object beyond the balance point, and then when you release it, this one got up and down. This is called harmonic motion. They follow the position. This is at 0, and here maybe like as t, right? The time, how far away from here to here. This follow this function, okay? They give this function. This is called harmonic motion. And when you have this harmonic motion, they will have follow. So they ask you to find what here? Use a table of the velocity to estimate the V0, means the velocity at t equals 0 at the beginning. So what we're gonna do is this. We can use the 3.5 equation. We can find out velocity at t equals 0, same as the derivative, the function, position function, t equals 0 like this, right? And then this one equals limits t approach to 0, and f t minus f0 divided by t minus 0 like this, right? And then from here, we can plug it in. So this is the limits t approach to 0. ft here is what? Just sine t minus f0. f0 sine 0 is 0. So that's why this is, I can put sine 0, okay? But sine 0 is 0 though. And t minus 0, just t. So from here, you can get what? Limits t approach to 0, sine t over t. Okay. Now, actually, this is a very important formula in the pre-calculus. We'll learn that. So this one will be equal to 1, okay? But how do you get that one? We can illustrate this one by using what? Table here. All right, as what I showed you, we were using what TI-84 to do this one. You see here, this is 0. We can get easily to get the table at each individual time t equals negative 0.1, negative 0.01, like that, right? We can easily get all this function value here also. And then we just observe that from here to here to here is closer and closer to 1. And from here to here to here also getting closer to 1. So that's why this one equals 1. 1 t equals 0. Okay, so this part is about how do we use the table to find this instantaneous velocity at t equals 1. Of course, this is just the estimation, and then we can use this one to find the answer. Of course, and if you do this one here, use the equation as what I wrote it here, you can directly get this one equals 1 because this one equals 1. This is a formula. All right. And then we're going to move on to this part here. So we just remember for the tangent line slope, same as instantaneous rate of change, and same as if it's motion particles. And this one, if it's a linear motion, we're talking about simplest case, okay? So that will be what? The velocity related to time, okay? So now I'm going to show you to do the check 3.4, all right? It said a rock is dropped from the height of 64 feet. Its height above ground is at t equals 0, time equals t seconds. Later is given by this. This is directly the formula from physics, okay? This from Newton physics here. This is mechanics, the motion, all right? So when you have this one, and we're gonna do is what? For find the instantaneous velocity of 1 second after drop. So what we're gonna do, we still follow the definition of equation of 3.5. So we can find what? The velocity, right? Of t equals 1. This one will be derivative 1t equals 1, like this. And this is definition will be the limits t approach to 1, right? And then you have st minus s1, st minus s0, right? From beginning to 1. They also told you that instantaneous rate of the t. So this one divided by t minus 0, okay? So from here, we can get what? Limits t approach to 1, st is this one, which is negative 16t squared plus 64, okay? And the minus t approach, oh, here, this is a 1 here, my bad here. So this one should be 1, because we're approaching to 1. We're talking about the value of 1 there, okay? So this one should be 1 here. So when you have this one, minus s1, right? S1, let's calculate it here first. So that's negative 16 times by 1 squared plus 64. So you can get, let's get the calculator out. So this is actually you do what, 64 minus 16, you will get 48. So this one equals 48. So this one equals 48. And then we divide it by t minus 1 like this, right? And the 64 minus 48, 64 minus 48 equals what, 16. So you will get like this. So continue go this part. It's a limit t approach to 1. And this is negative 16t squared minus this is plus 16 divided by t minus 1. Of course, right now you cannot plug in the t equals 1 at this moment, right? So what we're gonna do is a factoring now. Okay, let me just try to factor this part first, okay? This one we can take out what, the negative 16 out, okay? We'll do that. Negative 16, take it out. So you're gonna have a t squared here minus 1 like this. Be careful, huh? You take the negative out, here should be positive. It was positive, must be negative because this one times this one is negative 16 t squared. This one times this one will be negative, negative, positive 16, okay? And then this one is t, 1, I can write it as 1 squared, no problem. So you can write it as negative 16. This one is difference of 2 squares. We use many times. We have used many times about difference of 2 squares, okay? So you can get what, t plus 1 and the t minus 1 like this. Now I'm going to put it here, okay? Limits and t approach to 1. And then we have negative 16, t plus 1, t minus 1, okay? Over t minus 1. You see here, the beautiful part is that these two cancel. So you're gonna have limits t approach to 1, negative 16, and t plus 1. Now, you plug in t equals 1 here, 1 plus 1 is 2, times by negative 16 is negative 32. You see? Here, we use the definition of derivative. We can find out the velocity at t equals 1 if the object do the free falls. This formula from the free falls, like a drop, okay? On the ground, on the earth. Okay, so you can get this one. All right, so we can find the velocity now. That's very good. And we can see that, you see, when you study, this is the AP calculus, right? When you study the AP, there was AP physics. And AP physics, there is a C there. That's, it's called calculus base of the AP physics. That's the time, after you study this one, you can go to take the AP physics C. Okay, that'll be good. And here, so here we got what? Instantaneous rate of change of function at a value of a is derivative. So remember, slope of tangent line, instantaneous rate of change, and the velocity at a certain time will be the same, belongs to instantaneous rate of change. All right, just the real situation changes, but the mathematical model will be the same. All right. So today we just finish up to here. Next video we will cover about from here, example 3.8. Okay. And if you have any questions, please let me know. All right. Thank you. Bye-bye.